If you've been following my exploits with amplifiers lately, it shouldn't be a surprise that I'm planning on delving into this Kalamazoo Model 2. I love the sound of this tube amp. It doesn't have enough power for me, but we're going to get busy taking things apart, checking on the health of the tubes, and I know there's a hum on the power supply, so we're going to be changing electrolytics, that's for sure. New project, old amp. I already had to, it's so messy here, man, I got to vacuum it out, and I already sprayed like a spider web out from the input jack, so it's going to get loud. Turn down the volume. Couple of notes right off the bat. I lent this amp to a buddy when his son was thinking about maybe he'd be interested in playing guitar, so we wanted him to have something to play through. And so I think he did me a good turn. He replaced the cord, put on a really nice beefy long line cord. Looks like it ties off to the ground plane here with kind of a loose screw execution. That might cause some of the hum that I was hearing. I'm still going to change the electrolytics. It looks like, there may have been some recapping that went on in here already. I don't remember doing this. I messed around with this a bunch, hacking around when I was getting started messing around with electronics 40 years ago. I don't remember doing this. Now, he may have actually recapped this to some extent. I see a lot of orange drops in here, so they could have been vintage. I'm not sure. But, the thing that most impresses me about this amp right now, I love the tube sound, there's that, but the thing that most impresses me is the stench. It just has that mildewy, moldy smell to it, and deep in the corners there, even though I've already vacuumed this, there's some stuff going on I'm not too happy about. So my thinking is this might be a bit of a repackaging project. I can easily make some side panels, top and bottom, even if I dovetail them in, which this probably wasn't a true dovetail. And make a nice case for it, maybe upgrade the speaker a little bit in the process, and recover. He has a life of his own. Recover some of the glory of the tube circuitry that was. So it's like peeling an onion, man. And here's a very cool find. I knew I had a schematic for this somewhere. I was wondering where it went. It was right in here. So I think I'll carefully take the staples out, pull it out, and try and get a clean, high contrast image of this for my own purposes, and maybe share it. So we knew it would come to this. I pulled the chassis out of the Kalamazoo Model 2. I've got it up on supports. There's the tubes and the transformers. This is the power transformer. This is the impedance matching output transformer. Backside of all the controls and the input jacks, fuse and neon indicator light. Here's another view of the unit as I've got it set up on the standoffs. And this will give me access to work back here, clean things up a bit. I don't even remember replacing the capacitor a while back. This is the broken off stud. This rivet used to hold a 3-stage, what is it called, a 3 separate capacitor tube. So it had 3 different capacitor values in one unit, electrolytic. And I guess it must have been me years ago to replace it when it was going bad, I put in these separate 3 capacitors. So it's probably been another 30 or 40 years, I don't know, 30 years or so since then. I hate to say. It's been a long time since then. So another recapping makes sense. I'll put in some fresh ones. I'll look at doing something more extravagant, like whether I want to use a piece of perf board or printed circuit board or something mounted on here to straighten things up a bit. But the point-to-point wiring works pretty well for these. I might just stay with that. Hey, I'm really excited to move forward on this Kalamazoo project, but I'm waiting for components. This is not plugged in. I wouldn't be sticking my fingers in here if it was. And always make sure your electrolytic capacitors are discharged. Some circuitry will allow them to stay charged for a long time. You can really get hurt from that. You could get killed from lethal voltages. So know what you're doing. I ordered some electrolytics to replace these guys. And I also ordered a couple of tubes. They haven't arrived. So I need to do something about this cabinet. It's in really rough shape and it stinks. I'm going to basically build a new cabinet. So one thing I can do with the electronics for this Kalamazoo while I'm still waiting for the electrolytics and the tubes to arrive is make some baseline measurements. Right now I have a 5 millivolt RMS signal coming in to the amp, and I can measure the voltage across the speaker as a function of volume level. I'm not going to go very high in volume because it gets very loud and it gets very annoying. So I can use my Dale resistor for my output load, do an A-B comparison with when I get there, and then go up to maximum volume, record what I get for voltage on the output, and then when I put in new tubes I can compare the performance, sort of using the amplifier as a tube tester. Hey, I'm moving on to some calculations based on this baselining. I've got the Dale resistor in place of the speaker now, so this is strictly an 8 ohm resistive load. I have measured 656 millivolts across the Dale resistor. So there is a difference between this strictly resistive 8 ohm load and whatever the resistance of the speaker was, which is supposed to be about 8 ohms, but it has inductance as well. That can affect this measurement. Let's see. Also, I'm measuring RMS voltage with a multimeter at 1 kilohertz. I haven't done a scan to see where its 3 dB roll-off point is. I should do that. But I have corroborated with the oscilloscope measurements, so 650 millivolts is probably just about right. When you're making these power measurements and something doesn't seem right, you have to really start questioning. So I knew I was going to measure the value of this Dale resistor. When I measured it as I had it hooked up, it looked like it was like 12 ohms or something. Crazy. Well, I just tested this cable. The Dale resistor is fine. I put the test leads directly to it. I get 8 ohms. This cable right here is measuring 3.6 ohms. I have to repair it. So this is out of my corral of reliable cables. Okay, now I have my cables set up so that my test leads to the DVM through my 2 connection cables. I read about 8.6, 8.7 ohms through this Dale resistor. So that's an acceptable little bit of additional resistance thrown in from these cables. And yeah, there's 8.6. So that's acceptable. Just a few tenths of an ohm per cable. So now I can use those to measure power dissipated in that resistor. This is how the voltage comes up on the amp. It's been turned on for about 5 seconds. So I have reliable test leads going to the components here now. And I can always check to see if there's any difference if I wiggle them a little bit. Make sure I've got a good connection. I don't see any major changes. So I have 580 millivolts into an 8 ohm resistor. Here's the surprising thing. I'm only getting 580 millivolts across the Dell resistor and roughly the same thing across the speaker. So when we do the calculations, if I put say 0.58 volts and I square that and then I divide by the resistance of 8 ohms, I get 42 milliwatts. So not nearly enough. So I've swapped the output of the amp to the speaker. You hear the hum? I'm going to turn the volume up and measure the voltage dropped across the speaker. You may want to turn down the volume on what you're listening on, because as I turn this up it may get a little bit loud. So that was 630 millivolts. And let's see, if I take 0.63 squared, divide by 8 ohms, that's about 50 milliwatts. So nowhere near enough. Hey, guess what? My tubes and capacitors came in. So I'm going to put the cabinet work on the back burner for now. I'm going to work on the electronics. This is plugged in, so I don't want to be sticking my fingers in here and get electrocuted. You be safe at home if you try any of this. I was baselining with the existing tubes. I haven't changed them yet. And I'm going to do a little bit more baselining because it hit me that I wasn't pushing the amp very hard. If you think about the 50 milliwatts that I was measuring into the speaker and roughly that into the 8 ohm resistor, that's a drop in the bucket, and it all gets down to what the injected input voltage was. I chose 5.9 volt RMS for my input because that's close to the 5 volt RMS that I've used for some other amplifier projects, because the schematic says to make your measurements there. But in this case, I'm interested in seeing sort of what the max is that I can get out without a lot of distortion, and then with some distortion, I guess. But so it would be useful to crank up the input voltage to the point where I start seeing some distortion, or see a leveling off in the output power. I ordered a 12AX7 and a 6BQ5, and I got an ECC83S and an EL84. Those are direct replacements. I'm okay with that. So there you go. If you're wondering about the subdued lighting, I'm just trying to set a mood. The fluorescent unit that I have used for years is finally giving out, and you may see a flash from it every now and then. You may have noticed some flashes in a previous video. I'll have to look at that. It might be expedient just to throw a fresh tube in, a 4-foot tube, 40 watt, cool light. Well, here we go. I'm baselining the original tube complement in the Kalamazoo amp. I don't know if you can see this. I'm reading 82.2 volts RMS across the resistor, the output resistor, but this is with the volume all the way down. Crank it all the way up, and I get to 567 millivolts RMS across the resistor. I have arranged to be able to measure the input voltage by plugging in this BNC adapter, and the input voltage reads 5.7 millivolts. So what I'll do initially is just crank that up a little bit. Let's go to 20 millivolts. That was a flash from that fluorescent light. What a nuisance. So I've got 20.4 millivolts going in. And my output reading is now at 1.92 volts. So if I do a little quick math on that, 1.925, I square that and then divide by the 8 ohms, that's about half a watt. I need to keep playing this game with the input voltage and keep coming up with that and see what I track for my output voltage, and I'll make a chart of that. Hey, my tests on the output of a guitar show I can easily get about 100 millivolts RMS into my meter. right out of the guitar with the volume turned up, and through a pedal easily get 180 millivolts, probably more, staying a little conservative on the level out because that's where I tend to use it. But anyway, I'm emboldened to go up to 100 millivolts or so pretty directly. So I'll do it in increments. I'm up at 30 millivolts input now, and let's get a reading off the amplifier output into the resistor. Be nice to have a second meter or use a switch. That may come in time. And I've got 2.8 volts. Alright, so let's see what that means in terms of power. 2.8 square. It's going to be around 1 watt. Divided by 8, it's 0.98 watts. I'm at 40 millivolts input voltage, and my output is 3.656. One interesting thing is they talk about microphonics in tubes. This is almost an opposite effect. This 1 kilohertz signal I've got cranking in here now at 40 millivolts. I can actually hear it, even though I don't have a speaker hooked up. That pure 1 kilohertz tone, I know it. And I can hear it through some element in this amplifier. At 50 millivolt input voltage, I have 4.33 volts out into the resistor. I've taken my data at all the points in between, but wanted to point out with an input voltage of about 90 millivolts RMS, I had 6.0, what was it? 6.08 volts. It slumped a little bit, but that works out to be about 4.2 watts, and this is just starting to get a little bit noticeably warm. To deal with the heat from the power resistor, use a little bit of this compound, thermal compound. Slathered it on here. If I've ranted about this stuff before, I apologize, but it's messy, it gets everywhere, but it does a great job. There are alternatives that I use in high tech, but for home use, I've got it. So that's all. Now I've gotten up to 150 millivolts on the input. I was reading 6.86 volts on the output. I haven't done the power calculation, but I want to look at the trace. Hey, I wanted to give you a little update. This trace looks pretty good. This is with 56 millivolts input voltage, and the output voltage is, let me see, around 5 volts. So what I'm reading here is 5 volts per division. So an easy way to convert peak voltage, which in this case is about 7, to RMS is multiply by 0.7. So that's 4.9. It agrees with the RMS reading from the meter. The point I wanted to make was I found that there's a problem with this volts per division switch, so that at times it goes into, it's intermittent, and at times it shows garbage. So the other difference, I mentioned there are a couple of differences. The other difference from the way I was measuring this before is I'm still doing the differential measurement, but I have ground connected to one side of the output transformer. So that kind of cleans it up a little bit. So here is the output curve. The red is the power, the blue is the voltage, and I've plotted those parameters as a function of input voltage in millivolts. So we see at about 70 millivolts where we saw the waveform start to get hinky. That's where it rolls over. We know where distortion's kicking in, and we've baselined this amp pretty well. So it's not real scientific, but at least we have some numbers to go by. And the next step is to swap the tubes and see what that does. Here's the new ECC83S replacement for the 12AX7. Looks a little bit fatter. we're going to pop that in and see what effect it has alone, just changing that. You can see a lot of difference. Similarly rated though. What are my findings from all these voltage measurements? Well, to put it simply, there's no improvement by using the new tubes. May as well stay with the old tubes for now. I plotted out the characteristics. The blue line up on the top here is with the old tubes. So, I only changed out the one position for the 12AX7. I can play around with the one that's used for the tremolo and see if that makes any kind of a difference, but I don't expect it to. So, again, keeping it simple, sticking with the same tubes. The next step is to change the electrolytics, try and get that hum beaten down, and pretty things up a little bit. And then I'll take a look at that point at whether I want to use the unused portion of the second 12AX7 as a drive or more gain. Before I move on to replace the electrolytic capacitors, I wanted to check the tremolo circuitry, and I'm currently getting, with my 1 kilohertz signal at about 40 millivolts in, I'm getting 3.77 volts out. And monitoring it on the scope trace, when I turn on the tremolo, I get the typical pulsing that you would sort of expect for a tremolo, where you're basically putting an envelope over that. And then as I turn it up in frequency, it does what it should. It goes faster. But when I go all the way up, it just restabilizes. Not the way it should behave. I should be getting a very fast compression of the amplitude, and I'm not seeing that. So it also recovers when I turn the potentiometer back down. So the high frequency part, where I guess the resistances are lower, it's not doing its job. So it's acting like a capacitor is charging up and staying charged. I'll have to do a little troubleshooting on that. This is how things are going. I've removed the capacitor that was spanning across the bias resistor in the cathode of the tremolo tube. It was old and it looked like it was feeble. That part of the schematic, it's this resistor here, and that's the capacitor I replaced. So it's in there, and in order to get a clear shot at it, I went ahead and desoldered the plus side of the big electrolytic, and that made room to get in there. Replace that one. So I've already replaced that big electrolytic, and I did a little bit of work on the dress of the leads to make things a little better in there. And what remains is to replace these two electrolytics. So I have to get them to span from here over to here. So I probably will be using the axial lead electrolytics for that. Here I'm just about finished with the electrolytic capacitor replacement. I freed up some space over the V3 tube 3 socket by running a ground wire from this ganged ground here over to the center lug of this terminal strip, and I'm using that as the common tie point for both these capacitors. This one has one lead soldered in, the plus side lead. The two negatives come together on this center point, and that's where the black lead comes in to go over to here. It's a 22 gauge wire, I think, so that should be plenty. There's not a lot of current. And what I'm doing here is just final, not really lead dress, but just getting the capacitor lead set. So I'm bringing the soldering iron and apply some solder. This point-to-point wiring, you use a lot more solder than on a PC board. So we're going to get a good quantity of solder in here. You want to fill the loops that you've got formed in the wires, and you want to fill the hole that goes through the terminal block. There we go. Good hot solder joints, and when you put those wires through, you just want to crimp them enough so that they don't move while you're soldering. Alright, so that's the replacement electrolytic for the grid bias resistor on the tremolo circuit. I went ahead and touched up all the solder joints on this tube 2 or tube 3, and everything looks pretty good over here. These capacitors will be changed if this didn't fix the tremolo circuit, but I think that'll do it. And then now that with these the two 10 microfarad and then this 22 microfarad in here, these are the high temperature radial lead that I've sort of sprung out to do the job here, and 105 degree caps. What an amazing difference. Changing the electrolytic caps took care of a lot of problems. The ripple on the DC supply line on the after the first stage of filtering was 14 volts peak to peak. It's down to 4 volts peak to peak, which is, so if you take 2 volt peak times 0.7, it's about 1.4 volt RMS. That's a lot better than it was. The waveform looks a lot better too. It's just more solid. What I'm displaying is the output voltage. I'm using differential mode again, even though I have one side grounded on that output transformer lead. Anyhow, what we're seeing here is 1.5 volts RMS at 20 millivolts input. And when I crank up the input voltage, watch the trace. I'm going to just go ahead and sweep it up to about the roughly 100 millivolt input level. And even though I'm looking at output, I know what input causes the output. So that's approximately 100 millivolts input. You can see that it's clipping. And when you're playing your guitar, that gives you a cool sound. But it's pretty solid. So as I come down, it looks a little bit more like a sine wave there. And that would be at 5.9 volts is about 45 millivolts input. So that's 45 millivolts of input is where I'm going to start getting into a little bit of distortion or clipping. Now then, the tremolo circuit's fixed. That electrolytic on the bias resistor on the cathode was the culprit. And that's what it looks like at low speed modulation. That's faster. Nice. Notice you get a more profound effect when you're not clipping. Alright, the next thing to do is to do the play through the speaker listening test, and then I've got that cabinet work to do. Just one other thing, let's see, so I'm at 5.8 volts output right now. If I pull the jack from input 1 and put it into input 2, instead of 5.8 volts out I get 3.5, which makes sense because there's a resistor that goes to ground on the input 1 if there's nothing in input 1. So when you're playing through this channel all by itself, you get lower output power. Give you a quick description of what I'm up to here. I want to go through and make DC voltage measurements because after recapping this amp, I'm getting such better performance. I want to know what the voltage levels are. I had previously measured them. I call it VA, B, and C. So let me see. VA is the first voltage coming out of the rectifier with the 20 microfarad capacitor. Then I go through a resistor to a 10 microfarad. That's VB. And then a 100K resistor to a 10 microfarad capacitor, and that's VC. So VA, VB, and VC. And when I previously measured them, I found for VA that I had 279 volts DC. Don't know if you can see it. 271 volts for VB, and VC was 219. So we want to compare what we're getting now. I've got the black lead of the DVM attached to the ground, and then I'll probe with the positive probe. And this is where you have to be really careful. Keep one hand in your pocket. Just only use one hand when you're probing. If you slip, make sure you recover quickly and don't grab anything. I have no input into the amp right now. There's not even a jack in here, so I have also the volume control at 0. The next measurement will be the same condition, but with the volume at max. Then I'll put in a signal, 20 millivolt RMS input signal with the volume at 5 and then at 10. And then a 60 millivolt input signal at 5, and then the same 60 millivolts with the volume set to 10. This is all into an 8 ohm resistor for a load. So let's get started. And I won't take you through the whole series, but I'll tabulate this and I'll throw up a graphic showing what the values are. So for VA, I have 280 volts, 280.5. Now I have to decipher which is which between B and C. I've got 275 there and 218 there, so we know which is which. So that tells me right off the bat that the voltages aren't dramatically different, even though the performance certainly is. So now I have no input with the volume at max, and again I'm getting 280 here for VA. VB checks at 275, and VC, not altogether surprisingly, is still at 218. I'll continue, and as I said, I'll share the graphic with you when I'm done. This is to give you a better idea of the performance of the repaired tremolo circuit. The oscilloscope input is set at 2 volts per division. DC scale, I'm getting about 2.5 units above and 2.5 units below, for a total of 5 units or 10 volts peak to peak. This is with 60 millivolts into the amp. I don't have the volume all the way up. As you can see, I could go higher, but I want to avoid clipping so you get a better idea of how the tremolo works. So here's tremolo on, and then I'll go up in frequency. There you go. Okay, I've plugged the effects pedal in, the overdrive pedal, and I've just got the volume set at 7. I've got the tone set at about 7, and clean, it sounds like this. Kick in the drive. Pretty cool. Oh, and let's check out that lead type stuff.